Okay, a very welcome to all of you. And in continuation to the last interaction that we have had, in fact, we have been talking about the infinite potential well problem. We're talking about this problem, and we have discussed about this problem. And what we have a one-dimensional potential, and the particle is between the two walls, and these walls are basically representing the infinite potential walls, and you are telling a particle to reside inside this potential. This particle can move only from x equal to 0 to x equal to 3. And these two huge mountains of potential, what they do is they put their own constraints to the particle. And particle has to be in harmony, as we have talked about yesterday. And the particle will have some quantized energy states. We have already talked about the course of solving this problem, and we have reached to a point where we obtain the solution psi m equals under root of 2 by L sine of n pi by Lx. This is the eigenfunction, the general eigenfunction that we have obtained yesterday. And we would like to calculate the energy as well. But before going into the energy, there are some important things that we would be liking to talk about. The very first important argument is that if I take two states, as we know from the basic postulates of quantum mechanics, in a Hilbert space, these state vectors in the basis vector, they must be perpendicular to each other. They must be orthogonal to each other. And that condition of orthogonality tells us that the psi m psi n must be equal to 0. So this condition, we would like to verify this condition for this particle in an infinite potential box. Okay, that will be our target. So since we have already calculated psi, we can write down this bracket in terms of integration. So what will it look like? It will look like integral limiting from 0 to L, and you will have under root of 2 by L and sine, I will call it k mx to make my calculation simple. Okay, and then again you will have under root of 2 by L and sine k n of x dx. Okay, so this is your psi m, and this is your psi n, right? Okay, so this is what we would like to calculate, and we are calculating the orthogonality condition between the two state vectors in the given problem. So what we will get out from this is under root of 2 by L whole square. This will be outside the integral, right? And then you will be left with the integral from 0 to L. Then you will have sine of k mx and sine of k nx and dx. And we already know that this k is n pi by L, okay? So for Km, I'm using here m, and for Kn I'm using here n. Okay, so this is m pi by L, and this is n pi by L. Okay, so what we have here, we have sine theta and say sine phi. Okay, right? And you know from the basics of trigonometry that twice sine A sine B is cos of A minus B minus cos of A plus B. So from this we can take these two down. So sine of A and sine B will be cos of A minus B minus cos of A plus B divided by 2. Okay, so this is what we will use in our original integration that we have. So what we have here, we have 2 by L out. Okay, then you have integral 0 to L. Come on, you will have cos Km minus Kn x, right? Then minus cos of Km plus Kn x, and this is whole multiplied by dx, right? This is it. Okay, so what we'll get here, we'll get 2 by L is out. We have not yet integrated it, so we can integrate it. So give me its integration. Yeah, what will be its integration? Integration of cos is sine. Okay, so you will have here sine of Km minus Kn divided by the internal derivative of this Km minus Kn times x. What is that? That is Km minus Kn. Fine. Okay, then another part minus, this will be again sine, but what? Km plus Kn divided by Km plus Kn. Okay, and what is the limit? The limit is from 0 to L. Okay, something is missing. What is that? Here you have x. Okay, here you have x.
So 1 by 2.
1 by 2. Okay, 1 by 2 I can get that out. That 2 will cancel with this 2. Okay, so what we are left with? We are left with this thing. Now what we have to do? We have to give the limits. Okay, so look upon this integral that we have evaluated. When we'll give the upper limit, look at this. So when we'll give the upper limit, this x will be replaced by L, isn't it? And that L will cancel with this L. Clear? And here again, this x will be replaced by L, and that L will be cancelled because you can have common L, that L will cancel. So what is happening in case when you give the upper limit? What you are getting? You are getting sine Km minus Kn by Km minus Kn, isn't it? Okay, and then the lower limit, that will be 0. So the lower limit is gone. Okay, so again the same thing will happen here. The upper limit and the lower limit is gone. So I would like to directly write down what? The lower limit. Okay, what will be that? So what will be that? That will be sine Kn minus Kn divided by Kn minus Kn, isn't it? Okay. Okay, then minus sine Kn plus Kn divided by Kn plus Kn. Are you getting it? Okay. So this is our upper limit. In case of upper limit, that x is replaced by L, and L is gone. Now think about this. What is Kn? Kn is n pi by L. Okay. What is Km? That is m pi by L. Okay. So if I rewrite this equation, how will I rewrite it? I'll be doing, yeah, this is sine of n minus m times pi. Okay, there is L. Getting it? Okay, then in the denominator you have the same thing, Kn minus Km. I will not do anything here because I know what's going to happen. So minus, what we'll have here? Sine of n plus m, okay, pi by L, and divide by Kn plus Km. Now come on, you have a general expression for sine of n pi. What's that? That's 0, isn't it? So if you subtract the two numbers, whatever the number you will get, it will be multiplied by pi. So what will be its result? It will be 0. If you add the two, you will get 0. So what is the result? The result is 0. So this thing is verified for this problem, that the state psi m and psi n leads to 0. What does this mean? This means that the different states existing in the Hilbert space are orthogonal to each other. Now there is another important mathematical argument. Is say for example, it is the expectation value. Okay, the expectation value of momentum and the expectation value of kinetic energy. These are the two important arguments I would like to talk about. And once we talk about that, then we will try to have some kind of discussion, because what you will see here is, you will see that the expectation value of momentum is 0 for the first state, but you will calculate some kinetic energy. So that's a very fundamental question that will arise, that how can you have 0 momentum of the particle and at the same time it has kinetic energy? Okay, so that we would like to understand. So for that, let's go with that mathematical treatment. So the first thing that we would like to do is, we would like to calculate the expectation value of momentum. Expectation value of momentum. So how do you define the expectation value of momentum? That is psi and p and psi. Okay. So in fact, this psi n is psi 1 and psi 1. Okay. So I will generally take it as psi. So I would like to calculate this expectation value for the problem. The problem is already talked about. So how can I write down this? I can write down this as an integral from 0 to L, okay, and then under root of 2 by L sine of, I will again use that Kn of x to make it simple, and d by, then you have the momentum operator. What is that? That's minus IH bar dou by dou x, and then you have under root of 2 by L and sine of K has to be same here, okay? Okay, so we can keep K as here. K1, it is K1, so let me keep K for that, okay? So this is K and Kx and dx. Okay, so we can see this, we will have 2 by L outside, and inside you'll be left with 0 to L, sine of Kx, and this minus IH bar, I would like to write it outside. Okay, then the derivative of sine of Kx is cos of, so that is cos of Kx into the internal derivative of Kx, okay? So that K I will keep outside the integral, okay? So times dx. So what do we have now? We have 0 to L sine of Kx cos of Kx dx, okay? What we can write this? This is twice sine theta cos theta. What's that? That's sine 2 theta. Yeah. So here you can see what's outside. This is minus IH bar. K is there. 2 by L is there. And then you will have the integral 0 to L. And you have twice sine theta cosine theta. And that is simply equal to sine 2 theta. So here I can write down sine of 2kx. Am I right? Dx. Using this equation, using this formula, I can replace the internal of this integral by sine of 2x. And now I would like to integrate it. Okay? So the integration of sine theta is minus cos theta. So now, what's outside? Minus IH bar, yeah, 2 by L, and then you will have the integration that will be cos kx divided by the internal derivative of kx, okay, that will give me k, and what is the limit? From 0 to L. This is what we have, okay? So that's fine. Let's see what will happen now. So what I'll get is minus IH bar 2 by L, and K will be out. Now give the limits, okay? So you will have cos of KL minus cos of 0. Okay? But what is K? K is n pi by L. Okay? So K is, something is wrong here. I have missed something. This is 2 here. You remember the formula? This is 2 theta. Okay, so 2 kx, okay, so 2 was missing here, so here I'll be writing 2. So this is cosine of 2 kl minus cosine of 0. So what this will be equal to? Minus IH bar 2 by L k, okay, so this is cosine of 2, for k what I have? N pi by L, okay, times L minus cosine 0 is 1, right? So what you have here, this L and L will cancel, so what you have? 2n pi. So cosine of 2n pi is always, it's always plus 1, okay? So this whole thing will replace by plus 1, and what you will get? You'll get the expectation value of momentum. So for this ground state, psi, in fact you can call it psi 1, is equal to minus IH bar 2 by LK times 0, so that's equal to 0. So what have you calculated here? You have calculated that the average momentum of the particle is what? It is 0. Okay, now this is the first thing. Now let's go with the second thing. What is that? Kinetic energy. So for kinetic energy, what I need kinetic energy operator. And what's that? That is minus h bar square by 2m d2 by dx2. Right? This is our operator for kinetic energy. So what we would like to do now is we would like to calculate the expectation value of the kinetic energy for this ground state. So what will that look like? That will look like psi 1 k cap and psi 1. So what will that look like is 0 to L, yeah? You will have 2 by L outside because it's under root of 2 by L. The square of that square and root will cancel and you'll get 2 by L. And then you will have sine of kx and minus h bar square by 2m, and then the double derivative of sine of kx and dx. Right? This is something that we will achieve from here. So we would like to get these constants out. So what we will have this 2 and 2 will go, and you will have minus h bar square by yeah, this is m, okay, you're right, m and l. Okay, so integral you will have there from 0 to L, and then you have sine of kx. This is not the subscript, this is just a multiplied x, okay? Don't take it as a subscript. So you multiply it by x. So you take the derivative of sine kx, it will give you cos kx. Then the derivative of cos kx will give us minus sine kx, and that minus will make this whole thing plus, right? So what you will have here, you will have sine of kx. But you have to multiply the internal derivative of kx. So that will be k square, am I right? Fine? Okay, now this integral it's a very popular integral, and we know its value. What is its value? Do you remember? Okay, so I would like to write down this. So what I'm getting here is the expectation value of kinetic energy operator psi 1 is h bar square k square by ml. Okay, then you will have this is again what? This is twice sine theta. Okay? It is sine square theta. Okay, so this will be integral of, I should not use the bracket, this is integral of sine square kx dx running from 0 to L. So what you will have, h bar square k square by ml, and sine square theta is what? 1 minus cos 2 theta by 2. So we can do that thing. This is 1 minus cosine of 2kx. This is divided by 2. This is divided by 2. This is from 0 to L. And you have done this exercise many a times. And finally, when you give the limits after integration, after integrating this, I have not yet integrated it. Okay. Once you integrate it, from 0 to L, this term will be 0. The integration of this term will be 0, and you'll be left with L by 2, and this L and L will cancel. And what you have done is you have calculated the kinetic energy. Now this is a basic question. You have calculated the kinetic energy, and that is coming out to be h bar square k square by m. Right? 2m. Okay. Fine. And what about the expectation value of the momentum? The expectation value of the momentum is 0. That means the particle has the expectation value of momentum, 0, but at the same time, it has kinetic energy. So if we try to understand this thing physically first, physically, it's like this. If you draw the probability density for this state, what you will have the probability density will be something like this. So what does that mean? That means at the same time, the probability for this particle to be everywhere on this graph, right? That means, suppose this is the center, okay? Since we are dealing with a symmetrical situation, everything is symmetric here, okay? So what it is telling us is that the particle is having velocity in this direction, and it's having the same velocity in this direction, right? So since we are talking about the velocity is a vector quantity, the two velocities are going to cancel. That's why the expectation value of momentum is 0. Are you getting my point? So momentum 0 does not mean that the particle is at rest. The particle is everywhere in this case, okay? It is along right side, it's also along left side. So it has what? It has kinetic energy. Now let's demonstrate this thing to end this talk with our function. What is that? Eigenfunction, that is 2 by L sine of n pi by L x. Now what is this? This is sine of theta, right? So if this is sine of theta, I think we can write down sine theta in terms of exponentials. So can I write it as e to the power of I theta minus e to the power of minus I theta by 2. Now what does this e to the power of minus I theta mean? It means propagation in the right direction, and e to the power of I theta means propagation in the left direction. Are you getting my point? So for this sine theta, what will I use? I will use, okay, this is e to the power of I theta by 2 minus e to the power of minus I theta by 2. Okay, now we know what is theta. Theta is n pi by L times x. We will not go into those details. So what's going to happen? Psi n is what? Under root of 2 by L. Okay, then you have some integral. Okay, then you have what? Sine n pi by L times x. Right? And that I can write as e to the power of I theta by 2 minus e to the power of minus I theta by 2. I'm not going into the actual domain here, okay? Okay? So d, it is, we know it is dx. So I can represent this as this whole thing as psi right. No, this is psi left, huh? Because it's positive, huh? This is psi left minus psi right. So what is psi n? What is psi n? Psi n will finally give you what? It will give you the probability density. All you have to do is to multiply this psi n with its complex conjugate. And here we have a real solution. So that's why there's no involvement of iotars. So psi n is what? It is a superposition between the probability density in towards left and the probability density towards the right. Is this clear? Okay. So this is giving us a mathematical support of what? Why the expectation value of momentum in the ground state is equal to 0. Is this clear? Okay. Now what we have k equal to n pi by Lx. But what was k in the original differential equation? It was 2m e by h bar square. So now we can use here En. We can equate these two equations. Okay? We can equate these two equations and we will get what? We will get En is equal to, yeah, this is n pi by L, not x. Okay? K is n pi by L. It comes from the boundary conditions. We have discussed it in the previous interaction. So En will be what? It will be n pi h bar square by 2m L square. What's going on? Now this is k square. Okay? Yeah. K square is equal to 2m En by h bar square. So for k square, I will be using here then n square pi square by L square is equal to 2m En by h bar square. So what we are going to get from here is En. Tell me what is En. Yeah, what is that? En will be n square pi square h bar square by 2m L square. Now what is this n? N is an integral number. It's an integer. It's positive integer. Right? Okay? So if I take n equal to 1, what you will get? You'll get E1. n is equal to 1 means ground state energy. So E1 will be what? Pi square h bar square by 2m L square. What does it mean? It means this particle has the lowest possible energy. And what we call this lowest possible energy? We call this as 0 point energy. Okay? We call this as 0 point energy. The particle in this infinite potential well is dictated by these potentials which are infinite. They are dictating the particle how to behave in the system. Okay? They are dictating this particle. And this particle will not have zero energy. It will have a 0 point energy. Now, a question may arise in your mind. A question may arise, is E1 the ground state energy? Can't there be something like psi 1? This can be the question, okay? You can think about it. What about psi 1? Can't there be something like psi 0? Can't there be something like E0? This is something that rogs us. So if I write down my eigenfunction, what is that? Psi n is under root of 2 by L sine of n pi by L times x. This is it, right? Now, I would like to write down sine 0. What will be sine 0? It will be under root of 2 by L sine 0 pi by L times x, and this is 0. What it is telling you? It is telling you that these infinite walls does not allow to have psi 0. So if psi 0 is 0, there is no probability density of 0. If there is no probability density of 0, the particle will not exist in this state. Getting my point? That's why E1 that I talked about gives us what? The lowest possible energy, because there is not any other energy less than that of E1 which is available to this particle. So with this, I would like to end this talk. If you have any questions, you can ask me. Okay, thank you all.